Here we have a integrated rate law problem that has a couple of twists in it. First of all, they give us an equation for which there are two reactants, the oxygen atom and nitrogen dioxide. And then they tell us something interesting. The concentration of nitrogen dioxide was in large excess. So effectively what they're doing is creating a set of conditions so that the oxygen atom, the other reactant, is the only one that matters. If you saturate the solution with lots and lots and lots of NO2, then the reaction will proceed as quickly as the oxygen atom can be found or can react or bump into with appropriate orientation and energy the other reactants. So we'll approach this in much the same way as the previous question. We've got time data, we've got concentration data for the only reactant we have to worry about for now. We'll type that data into our stat edit menu, and under L1 manually type in all of the time data. This won't take long. And under L2 manually type in all of the concentration data, which again shouldn't take very long. Highlight L3 and set L3 equal to the natural log of L2, which is the natural log of the concentration of the oxygen atom. Highlight L4 and set that equal to 1 over L2, or 1 over the concentration of the oxygen atom. Make some stat plots. Make your X list L1, and your Y list, try 3 different kinds. Try L2, try L3, and try L4, but keep the X list L1. Zoom stat each time. Only one of those plots will give you a straight line, and the one that gives you the straight line will tell you what reaction order you have. As it turns out, we get a straight line, or the straightest of the lines, is found when we plot L1 against L3, which is the natural log of concentration versus time. Whenever that's the case, whenever the natural log of concentration against time gives you the straightest line, we have a first order reaction. And if they're telling us that in part B the reaction is known to be first order with respect to NO2, what's the overall rate law? Well, if we go back to the original equation, if I didn't have a large excess of NO2, I would have to say, okay, this differential rate law can be written as the initial concentration of oxygen raised to some power x times the initial concentration of NO2 raised to some power y. At this point, we know that the reaction is first order with respect to oxygen, so that means x is 1. And they're telling us right now that it's first order with respect to NO2, so that means y is 1. Well, the only answer choice for which the exponents are both 1 is the third one listed. If you can get that much of this question correct, then you don't really need to worry about this last bit. This last bit is a little bit confusing and tough, and I don't think you'll see it anywhere else in the course. But it is an interesting scenario. Let's go through this. First of all, they're asking us to find the rate constant K. Seems like a simple question. But if we know that NO2 is in large excess, as they say at the beginning of the question, at a concentration, we could say its concentration is constant. Yes, it'll change a little bit as it reacts away, but if it's in large excess, then it's not significantly going to change. It's still going to remain somewhere around, the number they gave us was 1 times 10 to the positive 13th molecules per cubic centimeter. And if we said, all right, from up above, we know that the rate is equal to some constant K times NO2 times oxygen concentration, then initial concentrations. And we doctored the conditions so that the only reactant that mattered was the oxygen atoms. Then effectively what we were observing is something a little bit different. What we were seeing is, let's call it doctored up K, or K prime, where the rate only depended on oxygen. And if you take that from the larger integrated rate law, we could say, okay, K prime is equal to the real rate constant K times NO2. So all of our calculator's work was finding the rate constant under these doctored up conditions. Well, go back to your calculator, go stat calc linear regression, and if you have a TI calculator, we're looking at the number that's represented by A. You may have to type in which lists you're finding a linear regression for, L1, L3. And after doing that, the value of A, or the slope, is roughly negative 100. Okay, so if the slope is negative 100, that means, if we go back to the integrated rate law, the slope is the negative rate constant, and that is negative 100. And this is all not K, but K prime. So K prime then is a positive 100 if we take the inverse of both sides. Okay, if we know that K prime is, as we had established up here, K prime is equal to the real rate constant K times the concentration of NO2, and we know that the NO2 concentration is constant at this really big number, 1 times 10 to the 13th, then let's take this expression and solve for the real rate constant. So take 100 divided by 1 times 10 to the 13th, and we get 1 times 10 to the negative 11th. The units here would be centimeters cubed per molecules per second. So 1 times 10 to the negative 11th. Now that whole last part, students, from here on, just consider this for fun. This isn't stuff I would expect you to be able to do on your own.